Hello everyone, my name is Syeda Hadi and I'm an undergraduate biotechnology student from Pakistan. So this year I had an opportunity to do an internship under the supervision of Dr. Jen Blank, and it was about designing a future habitat for 100 people on either Moon or Mars using AI tools. So my project is titled Beyond Earth, which is about designing a habitat in which humans can actually thrive on Mars. So my starting point was quite simple. Before designing a habitat, I needed to understand the planet it had to survive. So the story starts with a planet that does not want us there. Before designing the habitat, I defined the environment it had to survive. So Mars surface pressures is about 0.6% relative to Earth, and it has about 38% of surface gravity equivalent to Earth, and it receives around 43% of sunlight and as compared with Earth, and the approximate mean surface temperature there is around minus 63 degrees Celsius, and majority of the atmosphere comprises of carbon dioxide that is around 95.3%. Moreover, Mars has no global magnetic field, and its thin atmosphere provides limited protection from radiation and impacts. And water exists mainly as ice there, including subsurface deposits. So, a one-way journey to Mars typically takes around 6 to 9 months, and farewell launch windows roughly occur every 2 years, making frequent resupply impractical and requiring greater habitat self-sufficiency. So, why even are we planning to go to Mars? Why Mars? Earth is our home, but Mars is a frontier for scientific exploration, research, and technological development. Moreover, it can help us to prepare for long duration spaceflight missions and understand planetary evolution and how the environment can help the habitat to thrive there. Mars could also serve as a strategic base for assessing the resource rich asteroid belt, creating potential future economic opportunities. So the first question while designing the habitat was what must it be able to do? So mm, uh, these were the points that came into my mind. It should be able to protect the people from radiation, pressure loss, dust, and impacts. It should be sustainable, recycle air and water, and reduce dependence on Earth. Resupply. It should be able to produce food and generate power locally, and it should be able to support by providing healthcare, maintenance, and autonomous assistance. And finally, it should be able to give humans a sense of privacy, community, and a sense of home. This habitat will be a system, not a building. So I used AI for designing my habitat, and AI became my design tool, but not my designer. I used it to visualize complex ideas, rapidly explore alternatives and communication systems that are quite difficult to represent through conventional drawings alone. So my workflow was quite simple. I researched, defined requirements, generated prompts, and then images, and then I evaluated and refined and integrated. The important part was the evaluation stage. I researched the science first, generated a concept, then asked, does this actually make sense for Mars? If it didn't, I changed it. So AI helped me visualize possibilities, but scientific reason decided what stayed. So as you can see on the screen, on the left side are the images that I first generated for my habitat, and the tool used here is Gemini, and it is quite simple. And on the right side, you can see my final habitat design, where I incorporated all my creations into a collage, and it is a habitat designed for 100%. And I titled my habitat as Charbagh Mars Commonwealth. And one of the biggest decision that I took was to bring my habitat into a lava tube. So what is a lava tube? A lava tube is a naturally formed underground tunnel when the surface of lava flow cools and solidifies while molten lava continues to flow beneath it. So why lava tube? O- it helps to reduce the technical equipments we have to bring from Earth. So rather than bringing a quite lot of equipment from Earth and utilizing a quite lot of fuel for that purposes, why not utilize the natural resources found on Mars there? So that is why I incorporated lava tube in my design. Then for my agricultural concept, I took inspiration from traditional Persian and Indo-Persian garden design based on four special organization, symmetry, and a central axis. The growing zones are divided into four categories: staples, protein crops, leafy greens, and herbs, and diversity crops such as tomatoes, peppers, and berries. And the concept is based around producing approximately 250,000 kilocalories for 100 people with a substantial dedicated growing area. More importantly, the farm is designed as a loop. Human and plant waste becomes nutrients. Crew generates carbon dioxide that supports plant growth. Plants return oxygen, and water is continuously recycled. So agriculture isn't just a food source; it becomes a part of life support system. But a habitat can't only be addressed by biological survival. People still need privacy, identity, and personal space. So my private quarters therefore include a compact sleeping area, a bunker-style bed, a dedicated workstation, and biophilic components, a heritage corner that keeps Earth-link objects and personal meaningful objects inside the habitats, and a dedicated docking and charging station for um, the robot. And then there is the opposite of private space, that is a communal space. The communal areas are designed for shared meals, recreations, conversation, and collaboration. I incorporated elements inspired by Ottoman and Mughal architecture using a central space to create orientation and encourage social interaction. Plants and natural textures add biophilic elements to the underground environment. So power is the backbone of every other system. Um, as we all know that solar is a renewable resource, but since Mars only receives about 43% of Earth's solar energy, and the output is quite affected by night cycles and atmospheric dust and global dust storms. So my primary power system, reliable baseline power system would be nuclear fission, which produces electricity through controlled nuclear fission reactions and provide continuous power independent of sunlight. And it is suitable for critical systems such as life support, heating, communications, food production, ISRU. And the next question was that came into my mind was that who maintains the habitat when humans shouldn't go outside, and that is where Layla enters the story. On the left side of the screen, you can see my first generated concept for my robot, and initially it was named as Aegisward. Then I renamed it to Layla, and on the right side, that is my final design for the robot. And this robot is based upon the principles of biomimetics where there's gecko-inspired addition um, uh, of the robot for climbing and gripping, and then there's lotus-inspired dust repellent technology, and then there's rose petal-inspired gripping textures as well. And what it does, it basically is used for internal expansion and inspection, overhead maintenance, delicate handling, and proposed external infrastructure inspection. So autonomous maintenance can reduce human exposure to dust, radiation, and hazardous external tasks. So the second major problem is the one we usually forget. What happens when someone gets sick? So on Mars, Earth is not an emergency room down the road. At Mars, communication can be delayed by up to 22 minutes one way. Critical care cannot assume immediate Earth guidance. So my project proposes an Earth-built sterilized medical module that can support the crew during transit and then integrate with the Martian habitat. So the goal is not to bring a hospital to Mars, it is to bring a medical capability with the crew. My habitat extend beyond the lava tube through this rover. And the purpose of this rover is to explore, map, monitor, assist, and support astronauts during surface operations. So finally, I asked an important systems questions. What happens when something goes wrong? And my response sequence was detect, isolate, switch, inspect, and recover. Sensors detect the problem, and then the affected module is sealed to prevent a local problem becoming a colony-wide emergency. And then the critical services move to redundant power and life support pathways. And then robotic systems investigate external or hazardous areas before crew exposure. And then the crew repairs the affected module only after the environment is stable. So a good habitat is not one that never fails, it is one that can fail safely. So what would life on Mars actually feel like? First, a small crew would land on Mars, then a temporary outpost would be formed, and then there would be entrance to a lava tube established, and then pressurized modules will be established inside the lava tube, and then the system would be expanded, the agriculture system, medical and communal areas, and then an integrated habitat would be formed. And The final test would be, would people actually choose to live here? And that brings me to the real question behind the project. If humans ever live beyond Earth, what do we refuse to leave behind? The Charbagh Mars Commonwealth isn't only about regolith reactors, agriculture, or robotics. Its central spaces, community structure, and cultural references are an attempt to carry something human into an environment where almost nothing is familiar. We just don't need shelter on Mars. We need a home that can survive with us. Also, I would like to present a video that I compiled at a very last moment by using an AI tool. So, from surviving on Mars to living on Mars, that is the distance this project tried to cross. Thank you for listening to me.